Welcome back to The Explainer. Today we're taking a structurally fascinating journey deep into the cosmos. We're going to progressively zoom into a single point in the night sky to unravel a mystery that is quite literally challenging how we understand the physics of black holes.
Okay, let's dive into this. Take a look at this number. 65 million. That is the sheer, unfathomable distance in light years from Earth to our destination today. To put that into perspective, you know the light we are seeing from this object today? It actually began its journey right around the exact time the dinosaurs went extinct on our planet. Crazy, right?
So that ancient light belongs to this absolutely beautiful structure. This is Caldwell 29, or as it's formally known in the catalogs, NGC 5505. It's a weakly barred spiral galaxy nestled right in the Canes Venatici constellation. It was actually first spotted by the legendary astronomer William Herschel way back on May 1st, 1785. And you know, since then, it's been a prime target for stargazers. But to uncover the galaxy's real secrets, we have to look much, much closer.
Section 1. The Galactic Neighborhood. Let's look at Caldwell 29's immediate cosmic surroundings.
You see, Caldwell 29 doesn't exist in total isolation. It actually forms a physical galaxy pair with NGC 533. They share very similar sizes and mass-to-light ratios, and they're separated by a massive projected distance of 250 kiloparsecs. But what's really fascinating here is that despite being gravitationally bound partners, which was mapped out using radio data from the Arecibo telescope, by the way, their optical structures are completely undisturbed. So this proves that these two enormous galaxies haven't actually interacted with each other any time in recent cosmic history. They're basically just quietly coexisting in their shared neighborhood.
Section 2. Rings and hidden bars. Let's zoom past those outer spiral arms and get into the galaxy's complex internal gas dynamics.
And this brilliantly illustrates exactly what's happening under the hood. We have a spatial map of molecular gas near the galaxy's center. Notice that dashed line? That represents a hidden stellar bar, sitting right inside a larger 3 kiloparsec oval ring. This bar essentially acts like a giant cosmic conveyor belt, literally funneling streams of molecular gas inward, straight toward the galaxy's absolute center.
Let's walk through this progressive spatial disclosure step by step to really wrap our heads around the scale of what's happening. First up, we have that 3 kiloparsec oval ring, which shows clear non-circular motions. That means the gas isn't just orbiting peacefully, it's being heavily disturbed. Second, this massive disturbance creates a northwest gas stream moving radially inward at a blistering 200 kilometers per second. I mean, that is roughly half the free fall velocity. And third, all that infalling gas builds up into a massive 1 kiloparsec nuclear disk harboring a staggering 1 billion solar masses of molecular gas. And right at its core, there's a tiny 50 parsec depression, a molecular hole, just waiting to be filled.
Section 3. The X-ray core. Let's zoom all the way into that final 150 parsecs and see what is actually consuming all this infalling gas.
Now, what's really interesting about this slide is we are shifting entirely away from visible light. This is a deep, 255 kilosecond X-ray observation from the Chandra Space Telescope. That incredibly bright, glowing core proves without a doubt that a powerful, Seyfert-like active nucleus is lurking right in the galactic center, radiating intense, high-energy X-rays out into the surrounding space.
Breaking down this X-ray structure perfectly matches up with Hubble Space Telescope data. The diffuse, quote-unquote, soft X-rays, those with lower energy, under 3 keV, extend out to about 800 parsecs. Meanwhile, the much more energetic, harder X-rays are tightly confined to the central 400 parsecs. So what we are really seeing here is a compact, nuclear zone actively radiating and heating the gas around it, completely surrounded by a liner-like cocoon of excited, shock-heated thermal plasma in the interstellar medium. The engine is definitely on.
Section 4. The Black Hole Anomaly. This is where we hit the climax of our cosmic mystery.
So the crucial point is this. The central supermassive black hole is technically active, but it is effectively starving. We measure feeding efficiency using something called the Eddington ratio, and Caldwell 29 sits at an incredibly low 5 × 10 to the -6. That is a microscopic fraction of its potential. According to our standard astrophysical models, a black hole feeding this incredibly slowly simply shouldn't be able to maintain a broad, thin accretion disk. It should literally vanish into a puffy, diffuse cloud.
Let's move to and see how this builds when we look at the 3 competing models astronomers tested to solve the mystery of this central engine. They used high-energy data from the NuSTAR and SWIFT telescopes to figure this out. Scenario 1 is the black hole actually bright and feeding, but just heavily obscured by dust. Scenario 2, did it recently switch off, leaving behind just a lingering light echo?
Or scenario 3, is it an intrinsically low-luminosity system operating completely unobscured at a quiet whisper?
Well, the rigorous spectral modeling led to a definitive conclusion. As this quote highlights, the agreement between the observed X-rays and the predicted luminosities from the surrounding excited oxygen gas completely rules out a recently switched-off black hole. It hasn't died. Plus, the X-ray spectrum proved there was barely any obscuring dust at all. So the detective work solved the immediate case. It is absolutely scenario 3. We are definitively looking at an intrinsically faint, low-luminosity black hole.
But solving that just opens up a massive paradox, and this is exactly why this matters for you to take away today. We have an intrinsically faint, starving black hole, but the optical spectrums of Caldwell 29 clearly show a broad H-alpha emission line. Now, in astrophysics, that broad optical line is the unmistakable signature of a thin, fast-spinning accretion disk. It's a structure that persists despite the fact that our highly tested models unequivocally say it shouldn't exist at these extremely low feeding rates. It directly challenges our standard paradigms of how accretion flows work across the entire universe.
It leaves us with a profound realization. By zooming in 65 million light-years to the core of a single galaxy, we've found a genuine glitch in our understanding of physics. If a starving black hole, like the one in Caldwell 29, can somehow manage to maintain its thin accretion disk, what else are we getting wrong about the cosmos? Thanks for exploring the universe with me in today's Explainer.